Hello again, everyone. It's time to start Thermodynamics Part 1. We'll begin this off with a little cartoon there. I'll give you a second to read the cartoon at the top of the screen. It's a little morbid, but hopefully you guys enjoy thermodynamics more than what this cartoon is alluding to. Thermodynamics is a very big unit. We've broken this up into Thermo I, which we'll talk about now, and then Thermo II, which we'll talk about in the spring. The reason I'm doing this PowerPoint is because I'm not a huge fan of the way the book presents this information. It's not very consistently presented, and I've been doing this for a long time, and it has taken me a while to think through a logical, what is to me anyway, a logical progression of ideas as we go through this. So my PowerPoint is hopefully more organized than what you would get out of reading the book, although the information in the book is also pretty good, so I suggest you read it. Let's begin with some basic definitions. Thermodynamics, the very broad topic, is the science of energy transfer, energy of all types, which would include enthalpy, which we'll learn about in this PowerPoint, and then the spring materials, entropy, free energy, etc. Okay, so it's very broad. Thermochemistry is a subset of the study of thermodynamics. And when we talk about learning thermochemistry, we're talking about the energies evolved and absorbed by chemical reactions, the heat changes, the breaking and making of chemical bonds. That's the thermochemistry. That's the energy of chemical bonds. When we talk about energy, and we think back to pre-AP with those boxes, like in the gas laws where we had particles bouncing around if you did the FET. That's kind of the idea I want you to think when I'm talking about in a few moments here, systems and things. Inside any system, we have all these particles, and they're doing their thing. They're moving, they're bouncing, they're interacting. So the types of energy they have can either be kinetic or potential. If you've had physics, these topics are very easy to you. If you haven't, it's okay. You'll get to it. But just kinetic energy, energy of motion, and it's pretty simple. It's straightforward. The formula for that is one that you've probably heard. It's kinetic energy equals 1/2 mv squared. Very simple. It doesn't really change. Now, potential energy is defined as stored energy, energy available to do something. You can store energy in a lot of different ways. You can store it against gravity, like you hold something in the air. That's the one you used probably the most in physics. Or elastic potential, if you did any Hooke's law problems in physics. You can store either in a spring that's compressed or a string that's stretched or a rubber band or anything really that stretches. Electrical or electrostatic repulsion. If you've done any of the Ohm's law stuff, we talked about voltage. This is electrical potential, energy ready to go from one activity of another, or to a substance of another activity. And then we have chemical energy, which is really what we're looking at in this class. This is the energy stored in the chemical bonds. When we talk about energy, the units, just real briefly, are either the calorie or the joule. The joule is the SI unit. That's the one we'll be using in class this year. It comes from a derived unit. You can see here. If you take that kinetic energy formula I gave you earlier, it was 1/2 mv squared. So v, meters per second velocity. If you take that and square it, you get meters squared over second squared. And then, of course, mass is kilograms. And we make that derived unit into something a little smaller called the joule. Kilogram times a meter times a second is another way to write that. So kilogram times meter over second squared. I think I said second a moment ago, but second squared. It's another way to write this. So that would also be a viable way to express this. This term here, kilograms times meter over second squared, that's also in Newton. So that's where N comes from. And that's from physics. You did that when you multiplied m times g to find the weight, for example. The calorie is the older English unit. It's defined as the energy required to raise the temperature of water by 1 degree Celsius. We talked about that in pre-AP with specific heat. We don't use that in here, but unfortunately for you, when you get to college, most of your professors are still of the age when the calorie was the unit of choice. That has certainly been my experience in college, even recently at A&M Commerce. So they still love to use calories and mostly kilocalories. A joule is very small. It's even smaller than a calorie. It takes, as you can see in the third bullet, 4.184 joules to equal a calorie. And that number, that conversion, is defined by water, the specific heat of water. If you remember from pre-AP, the specific heat of water was 4.184 joules per gram degrees Celsius. That property is the definition of the calorie. One thing that students often have trouble with in this unit is differentiating between temperature and heat. That's because as you've grown up, people haven't really stopped you and said, hey, now those two terms are really different, but now it's time to make that distinction. We define temperature. Now think back to gas laws in pre-AP where we did this for the first time. Temperature is an intrinsic property of matter that relates to the random motion of particles, so the particle's kinetic energy. We've said that when things are so-called high temperature, that means the particles are really moving fast. And when they're at a low temperature, they're really moving slow or slower. So it has really nothing to do with hot or cold. Heat, on the other hand, is a transfer of thermal energy between two objects. Heat is much more difficult to conceptualize because it is a movement of energy. Now, I think here in this bullet you see here, treated analogously to electricity. You kind of have this idea of when you plug something into an outlet in the wall, electricity is going to flow from that outlet or high potential to the end of the cord, which is at a lower potential. And that's the same thing we have in thermochemistry when we deal with heat. If you touch something that's hot, the energy is going to flow from that hot object and its particles moving really fast into your colder finger, and there you have the flow of energy. So think about electricity, at least as you're learning this. Hot and cold are relative terms. They don't mean anything. As I said in this example, you touch a frying pan, it's hot, it burns your skin, peels it away. It's terrible stuff, don't do it. But if you're a person who's living on the surface of the sun, you're used to hot. So when you touch a earthling hot frying pan, it really doesn't mean much to you. All right, the first law of thermodynamics that we're going to deal with in this unit is called the zeroth law. You could also write that just as a zeroth with a zero instead of spelling it out. It's very simple. You've known this almost your entire life. The zeroth law says that energy transfers from high temperature to low temperature. If you touch something colder than your hand, it feels cold, and energy is going to rush from your hand into the colder object. If you touch something that's warm, energy is going to run from the warm object into your hand, and it's going to feel hot. That transfer of energy will continue until everything's at the same temperature, and we call that an equilibrium, and specifically a thermal equilibrium. This is problematic if you touch, again, a hot frying pan. All that energy, if you touch it, all the energy in the frying pan goes into your hand until it reaches the same temperature. When in the meantime, your particles are going to grab that energy and start moving around faster, their temperature is going up. And if they move too fast and have too much energy, then you will have the energy necessary to start breaking chemical bonds. And that's the actual act of burning and causing damage. As we talk about thermodynamics, we need to be really solid on our understanding of what a system is. So let's go through this. A system is very basically a portion of the universe. Now, I mean the universe, everything that we know. A system is the portion of the universe that you're singling out for study. Everything else are the surroundings. So the universe equals system plus surroundings. In bullet 2, the total energy lost by a system is equal to the total energy gained by the surroundings, and then vice versa. So there's an interplay between system and the surroundings all the time. Systems are either open or closed or isolated. Now, open and closed seem pretty simple. Isolated may seem a little weird to you, but we'll see what we can do. Open systems can exchange matter and energy. Look at the picture of the pans at the top of the page. The one on the right is an open system because there's no lid. Water can splash out, evaporate, whatever, so mass can be exchanged, and then also energy can be exchanged. So that is an open system. If you put the lid on it, you're stopping the water from escaping. So it is now a closed system. The energy change still takes place. It may be slightly affected by the barrier itself, but it can still take place. Whereas in an isolated system, you can't exchange either. My best example of this would be if you can think of something sitting in outer space, like a box in outer space. There's nothing around it. It's a vacuum. That's about as close to a perfect isolated system as you can get. So we're talking about energy exchange here. How do we exchange energy? Well, in here, it's work or heat. That's the way we're going to do it. I'm going to get more into those terms as we go here. You may be thinking, how do we define a system? Well, in chemistry, the system is usually just our reactants. Now, it's up to you how you define that. If you're looking at a chemical reaction, let's say hydrochloric acid plus sodium hydroxide, those reactants could be your system. Well, you think, well, they're in a beaker. What do I do about the beaker? Well, if you want to define the beaker as part of your system, you can do that. If you want to include the classroom as part of the system, you can do that. The problem you run into is that the more things you include into your system and the more complex those things are, the math gets really, really nasty. So for simplicity's sake, you want to make your system as small and exclusive as possible to do your work. So usually we're going to just focus on the reactants as being our system. Let's talk about work and heat now. Let's get the symbols out of the way. For heat in here, we're going to use a lowercase q. This is the same q you did used in pre-AP to do the specific heat calculations and the heat capacities. We're just bringing it along. We're using lowercase w as the symbol for work. Now I know if you've had physics, they were a little loose and free with the use of the capital W for work. Technically it's supposed to be lowercase, and that's going to be important here later. We define energy. You've had this definition since middle school, maybe even elementary: capacity to do work or transfer heat. If you've had physics, the next bullet's kind of useless to you, but work is the energy used to move an object against a force. So we know that when we do that, objects must move. You must move in the same direction as you apply the force, and then that definition can be summed up in this equation right here. Work is equal to force times distance. I've already talked about heat and the zeroth law, so I'll move on to the next slide. When we think of the systems, we often use a box, just a box. Some of you might prefer balls, whatever, as the system. Here I'm representing heat and work exchanging itself or transferring itself between the system and the surroundings. So you see Q's and W's both leaving and going into the system. That's important because there's a sign. We need to keep the sign convention for Q and W very clear. Let's look at this chart real quick. Work done by the system, negative. Work done on the system, positive. So I'm going to go back to the picture here. If I'm talking about work, if I do work on a system, that's this right here, I am putting energy into it. I'm working on it. And that's going to cause the energy of the system to increase. So we'll give it a plus sign. If that system does work, just like when you do work, you get tired, the system loses energy, so we give it a negative sign. Same concept for the heat. If heat is lost, we're going to give it a negative sign, and if heat is gained, we're going to give it a positive sign. So back to our drawing here. If I'm heating a system, like putting it on the stove, for example, heat is going in, the energy of the system goes in, so Q would be positive. If I let a hot cup of coffee sit out on the countertop, it's going to cool off because heat is being exchanged with the surroundings, so the sign of Q would be negative, and the energy of the system would decrease until it's at thermal equilibrium. These terms, you've known them for a very long time. We'll just hit them real quickly. Endothermic and exothermic. Endothermic processes are which the system absorbs heat. Q would be positive in that case. Endothermic feels cold to you. That's because heat is leaving your hand going into the system that you are in contact with. So it's going in. The energy of the system will actually go up. The energy of your hand actually goes down. That's why it feels cold to you. And then exothermic would be the opposite. Just remember the signs. Exothermic is negative for Q. Endo is positive for Q. Now we come to a new thermodynamic term for you here. When you look at a system, remember I said imagine like in the gas laws where you have this box full of all these little particles that are moving and bouncing around. Keep that concept in your head. The sum of all the kinetic and all the potential energies of every particle in the system, that is called the internal energy of a system. That is very, very difficult to measure. There's no such thing as a probe you can stick into a system and have it output an internal energy. The symbol for internal energy is either U, which you'll see in college more. AP, for example, doesn't use U that often. Most of the time they just use E for energy, and that keeps it a little bit simple. Now, it's very difficult to measure this, like I mentioned, but it's much easier to measure changes in internal energy because temperature can tell us a lot about the changes that systems undergo. There's two ways that the internal energy of a system can change: heat or work being done on it. So we have a little equation here to represent the internal energy of a system. The change in internal energy, because remember I said it's very difficult to measure U, but changes in U are much easier, is simply equal to the work done and the heat exchanged on that system. This expression is what we know as the first law of thermodynamics. Here's some real quick problems with first law. The hydrogen and oxygen gases in a cylinder are ignited. As the reaction occurs, the system loses 1150 joules of heat to the surroundings. The reaction also causes the piston to rise as the gas expands. The expanding gas does 480 joules of work. Okay, so we know that delta E is equal to Q plus W. All we do is sub in and make sure we get our signs right. So it says here the system loses 1150 joules of heat, so that's going to be minus 1150 joules. And then let's figure out the work. The gas does 480 joules of work, so that will also be the system losing energy, negative 480 joules. So if we work that out, looks like it's going to be close to 1600 and something. So 1630, negative 1630. I wrote right over my answer, but you get the idea. All right, you try this next one. Hit pause and then hit start when you're ready. All right, hopefully you got 55 joules for this example. Let's talk more about the first law of thermodynamics. The energy loss, it says that energy is conserved, the second bullet. That's really the key idea to the first law of thermodynamics. Energy lost by a system is gained by the surroundings. You can change forms, but the total will always be the same. So this little equation here is also a way to express the first law of thermodynamics. I know we already looked at delta E equals Q plus W, and that's also a way to express it. So it just depends on the application you're looking at. This is just a simple energy balance on a system. The total energy of the universe is constant. It can't be created nor destroyed. For systems, if we have an open system, we talked about how matter as well as energy can be exchanged, so heat and work are both important. If you're a closed system, not much work is going to be done at all, so the internal energy is equal to the heat change. And then for an isolated system, since you don't have any exchange with your surroundings at all, the change in internal energy will always be zero, which means any heat change within the system has got to be due to some work being done on it. So those two terms would be equal. At the top here, I've given you a link. If you want to now, press pause in this lecture and watch that quick video. This is from a professor at Cal Berkeley, and he does a pretty good job of going through this again. Hit play when you're ready for me again. All right, let's talk very briefly now about work. Work is the movement of an object over a distance. I'm hoping all of you have seen this in physics. We talked about a few moments ago about this definition of work. Chemical reactions don't often involve a lot of work, so this is not something we're totally worried about. Most chemical reactions occur at constant pressure on the desktop. Most of the volume changes are negligible. When we add hydrochloric acid to sodium hydroxide again, it's not like they're expanding and contracting. The volumes just add together. So really what we're worried about in chemistry for work is if we have gases, because we learned last year that gases can change their pressures and volumes very easily, so we have to take that into consideration with gas reactions. Here's a work problem. Let's see just real quickly. A bowler lifts a 5.4 kilogram ball from ground to a height. What quantity of work is used to raise the ball? Well, work equals force times distance. We can expand that. Since we don't have a force, I have a mass, but mass under the influence of gravity will give me my force, and then times the distance. So I plug in 5.4 times 1.6, and then times that acceleration of gravity, and that's going to give me 85 joules. Plug that in and make sure that you get that as well. And then the second bullet is another example problem. Assume no frictional effect. What is the maximum velocity? Well, change in energy of a system is also equal to the work done. So for this one, we just need to use the kinetic energy, since we're going from rest to moving. That equals the work, and you can solve for V. And you can solve for V because it is initially not moving, so VF minus VI is really what you're looking at here. So try that one and see if you get the answer. Okay, so this one is a little bit mathy here, so we'll walk through as quickly as we can. So what if we do have those gas phase reactions and Q plus W becomes tougher because we need something for that work term in a chemical reaction? Well, we're going to start with that work term, force times distance, and then we're going to replace it. From physics, maybe you learned that pressure equals force divided by area. If you don't know that, now's a good time to know that. So pressure is equal to force divided by area. Then we're going to rearrange that. And I'm going to solve that for F. Force equals pressure times area. Let's plug that new rearrangement into equation 1, step 1 up there. And now I have work equals P times A times D. Then I'm just going to group A and D together. Area is two-dimensional, so if I multiply it times another length term, that's now 3 dimensions, and we have now a volume. So that equation now becomes work equals P times a change in volume, or we mostly just write that as work equals P delta V. So we call that PV work in chemistry and physics. That term is going to be negative if work is done by the system, positive if work is done on the system. That's the same thing we did on a few slides ago when I was talking about the signs of these terms in a system. Nothing's changed. If we plug those into the first law, now the first law becomes internal energy is equal to heat and then the work term. And we have a negative sign here is because work done by the system. Gas expansion is most common. All right, let's go into enthalpy, which is one of our last few things here. Most chemical and physical changes that we have in chemistry occur at constant pressure. We talked about that. If there's gases, that's when we have to worry about the work term. So most energy changes in chemical systems is due to the heat. So that Q term in chemistry is usually, almost always, the most important. So we have a new term, enthalpy. Enthalpy is defined as the heat change of a system at constant pressure. If we have that constant pressure, then we don't have to worry as much about the work term, but we can use P delta V to take care of those gases that are expanding at a constant pressure. So a couple of problems this allows us to work would be like gas reactions in a movable piston or in a balloon, something that's allowed to change its volume and keep a constant, usually atmospheric pressure. So this is a very special case. So enthalpy is basically the heat change of a reaction, but it is constant pressure. If we have a gas phase reaction, we can't just say Q. We have to take the volume change into consideration, and we have to use this form. So just like heat, enthalpy has a negative value if it's exothermic and positive if it's endothermic. The symbol for enthalpy is H, kind of strange. I don't know what H means. Maybe I used to know, but I don't anymore. Like internal energy, it's very difficult to measure. So instead of measuring it directly, it's easier to measure changes in enthalpy. So that's why we have delta H. Enthalpy, like internal energy, I didn't mention it at that time, but enthalpy is a state function, so is internal energy. So that means it depends on the current state of the system, not what it used to be, what it is right now. Like internal energy, we saw a while ago that E was equal to E final minus initial, same thing for enthalpy. And enthalpy is an extensive property. So the more reactants you have, the more heat you can change in a reaction. So H, heat, is an extensive property. There's lots and lots of different types of enthalpy depending on what you're looking at. Heat is heat. So really all this means is that we can use different subscripts to tell us like what kind of change we're undergoing. For example, RxN is reaction. That's very generic. Any type of reaction, or if you're just not trying to be specific, just say reaction. F is for formation. That is a very specific type of reaction. That is defined as making a compound from its elements at standard conditions. So that is a formation reaction. This one is combustion, so it's also very specific. This means to react it with oxygen, to burn it. This can also apply to physical changes. Enthalpy is also associated with vaporization, fusion, which you might want to think of as melting, subliming, or even dissolving. So physical changes also have energies associated with them, and those subscripts just kind of tell us what we're doing. It's more information. The last thing is state functions. So I've given you a couple of videos to watch as well. You can either watch them before or after I go through this, but you need to watch each one. It's by Dr. McCord down at UT Austin. State functions are systems or properties of a system given by specifying its conditions. So just like a temperature, a pressure, how much mass does it have? How much enthalpy does it have? How much internal energy does it have? It doesn't matter what it used to have, just what does it have right now, at this time. In thermodynamics, the most common ones that you're going to look at are internal energy, either U or E, enthalpy, entropy in the spring, Gibbs free energy in the spring, and temperature all the time. Heat and work are not state functions, and those are the ones you have to remember are not state functions. If you don't know what a state function is yet, you can cheat and remember that if it has a capital letter, it's a state function. State capital letter, state function. And then A state function is path independent. It doesn't matter how you make the change, just that the change gets made. Internal energy is a state function. You have 50 joules at the beginning. You undergo a change. You have 150 joules. Okay, it doesn't matter how that change was made. Your change in internal energy is still 100 joules. Now, your heat and work can be very different than that, because maybe you heated it first, then squeezed it a little bit, and then cooled it down. Or maybe you just heated it, and that's all you did. Or maybe you did some work on it, you carried it up the stairs, down the stairs, across the hall, then heated it up. So the way you do it could require vastly different amounts of heat and work, but ultimately that change in state of the system will always be the same. So watch that video here, also by Dr. McCord, about changes in state. In the very last slide, I promise, how is enthalpy measured? Well, you can go to the lab and you can do it by hand. The measurement that we always make is temperature. So the technique is called calorimetry. You're going to do a couple of labs this year, and depending on who your teacher was last year, you may have done one already. So you just go to the lab, you do the calorimetry, measure delta T, and you can do the calculations to figure out what your heat change is, and then whether or not it's a gas phase reaction would require a different type of calorimeter. Or you could use heats of formation. So we're going to do some problems like this, where you go to a table in the back of the book and you're going to pick out some values of heats of formation that have been discovered many, many years ago and are recorded, and then everyone can use those. Or a third option is to use reactions that are already measured and known and recorded as well. But let's just say, for example, we're going to do a lab on the enthalpy change for burning magnesium. Well, that's a very difficult reaction to measure temperature changes, because you have a solid and you have a gas, and putting a thermometer on a burning piece of metal is not very efficient. So instead of doing a calorimetry on that, we want to use Hess's law. If I can't measure magnesium plus oxygen goes to MgO, maybe I can do magnesium plus hydrochloric acid goes to magnesium chloride. And then maybe I can also use magnesium oxide plus hydrochloric acid goes to magnesium chloride plus water. And then maybe I can use H2 plus O2 goes to water. Combine all three of those reactions, flip them around, multiply them by factors, come up with it's like I put a puzzle together, come up with a reaction that's what you want, and then you can add the enthalpies up and it'll give you your reaction. This is a skill we're going to learn in this unit. There's an upcoming video on how to work those problems. But for now, either you measure it, or you can use known values of formation or known values from other reactions. Alright, if you have any questions about this, come by and see me. Watch it as many times as you need to. Make sure you watch those 3 YouTube videos that were in the slides.